Good morning, Professor Bari.
Namaste and greetings. I am so honored to be speaking here at Delhi Public School East Bangalore, and I thank you sincerely for the opportunity.
Yes, we will start the program, Professor. Could we? Ask the right questions, and nature will open the doors to her secrets. So, C.V. Raman. Namaskara. Greetings from Bengaluru to all our viewers. Welcome to the event. We begin with the opening remarks by Principal Mrs. Manila Carvalho.
A very warm welcome to the youngest professor, Subarno Isaac Bari, from Delhi Public School, Bangalore East Fraternity. Thank you for accepting our invitation and joining the event, an evening of physics at Bangalore, India, with our students. A very warm welcome to Mr. Rashidul Bari, the proud father of Professor Subarno, and thank you very much for facilitating this program. Every year, Science Week is celebrated to mark the discovery of the Raman effect by the Indian physicist Sir C.V. Raman. This year, we are very pleased to have amidst us the youngest well-known professor Subarno Isaac Bari, who has been accorded with the title Einstein of our times, to conduct a session for our students. A very warm welcome to you, Professor Bari, and we are looking forward to your session.
Thank you. I am so honored to be here at Delhi Public School Bangalore East and to be hosted by Principal Manila Carvalho. I am so grateful to all of you for allowing me the honor to speak here. And today, I would like to speak about a journey through math and science. Today, I will speak about a basic yet cohesive history of science, all the way from the ancient times to, you could say, the modern period, but it will actually end sometime around 1955. So, we will start with the story of how I fell in love with math and science. Let's rewind all the way to 2013. My father was a part-time security guard, but he was also a student back then. He was a student in mathematics, and so I would often watch him practicing mathematics on the blackboard. And I was so fascinated by that magic trail that he was always writing. What could those equations mean? I was just so curious about and fascinated about all the repetition, all the symbols, but yet while I seemed to recognize patterns, I couldn't get any sort of meaning out of the equation. And I was always so fascinated with them when I was young. I wanted to learn more about them. And so, thank you. And so, one day I wanted to do the same thing my father did. I wanted to write down these equations like with seemingly magic. And so one day when he left the room, I went toward the chalk and I tucked it under my bedsheet. However, the next thing I did in the morning was flail it around. Why? Because I had seen that I had broken the chalk into two pieces. With my little legs, I had crushed the chalk. And after that, When my mother tried to change the bedsheet, all she saw was white powder. However, that was how I fell in love with math. I was just so fascinated about the creativity, about all the symbols, all the building blocks. And to this day, I still fantasize using mathematics. I still think of negatives as positives of a fight of sorts, if that really makes sense. And so, I still make it easier for me to understand, and I hope that this lecture makes it easier for you to understand not only how I fell in love with math and science, but also a lot of things in math and science. Now, I fell in love with science much later on my second birthday. I was first exposed to science also when I was 1. However, I wasn't really interested in it as I was mathematics because I didn't like being limited by the natural world. I used to have this mindset when I was younger that science was boring because you had limitations here, there, and everything had to be like this and everything had to be like that. There was no freedom like in mathematics. However, now that I know there is so much freedom, so much that we have yet to explore, and so many more strange things in the world that we don't know about. We are trying to investigate. And that was when I fell in love with science. Back in 2014, on my second birthday, I woke up to have my father calling me outside. He called me to what used to be our garage. However, to my surprise, he had completely cleaned it out and set up a blackboard on the wall. There was also a table with a book on it. Of course, a small table for 2-year-old me. And the writing said, find the name and the writer of the book. Author was probably too small a word for baby 2-year-old. And find the name in the writer of the book. Have one out. And so I got to it. I looked around, thinking that maybe it was a scavenger hunt. Maybe I had some paper slip here or there. However, after a few minutes of investigation, I realized it was something completely different. After about, say, 10 minutes, I realized I only had 50 minutes left. It's basic math. I also realized that there was no scavenger hunt. Rather, you'd have to use science in order to get forward. And so, I flipped through the pages, waiting for the answer to come to me. And after not a lot of flipping, on page 6, I found my savior. It was a picture of a schematic of the Earth. I know picture schematic doesn't exactly make sense. A schematic of the Earth with a cannon on it that was shooting cannonballs at large speeds, to say the least. And this cannonball was getting increasingly farther, taking more of a parabolic path around the Earth, until suddenly it had so much velocity that it escaped the pull of the Earth. And so I thought that back then Newton came up with that, because I had learned earlier that Newton had thought about the apple and the moon, why the moon doesn't fall but the apple does. And now I was thinking about how the apple fits the how could you say it? Genre? Or the apple fits the narrative, you could say, of the early stages of the cannonball. However, let's say the moon could fit the later stages of the cannonball when it is in outer space or in orbit. And so, through this physics lecture, we will not only explain to you electricity, magnetism, the Maxwell equations, but also gravity. and the concept of gravity. However, that was when I fell in love with math and science. If you're wondering, I did put the author as Sir Isaac Newton. However, I did not put the name correctly. In fact, I thought that the name was Newton's Cannonball, which in fact, luckily, was the name of the Pixar. I did some fancy researching a few months ago, so I won in some way, but actually, it wasn't the name of the book. It was some crazy Latin thing that I can't bother to remember, but it was one of Newton's less famous works, if I say the least. So, now, that was the day I fell in love with math and science, and my trek through math and science has been a long one ever since. And so, my 10th birthday is coming in just over a few months, or 5 months to be exact. So, that will mark 8 years of studying math and science. And so, through my journey, I have been trying to form a cohesive history of math and science. And many times I have done this when I was younger, say 5 or 6, but I put in my own biases or didn't bother to research before I put my own opinion in. Now I have learned from those experiences, and now I have researched so much that I can consider what I have written to be accurate, accurate in a sense. And so, let us start in 600 BC, where the first known scientist, Thales, was. Thales was actually named Thales of Crete because he was born on, I presume, the island Crete in Greece. So, in Crete, he was a mathematician, scientist, philosopher, and engineer. And he is the first known mathematician, scientist, and philosopher. Why? Well, everybody else at that time, remember this is 2,600 years ago, everybody else at that time didn't bother to think why natural phenomena could be caused. If you ask them, why do things fall towards the earth? Why do they fall down and not up? They'd say, God. If you ask them why the moon doesn't just fall out of the sky if an apple does, then they'd say Theos, which is Greek for God. And so, everything was just God, at least to most of the people in Greece. However, the reason we remember Thales is not because he had particularly great ideas, but rather because he was the first, at least the first known person, to diverge from that divine explanation of sorts. And so, you may be asking, his ideas can't be that bad. I mean, yes, his ideas in math, at least his ideas in math, I feel like the most known idea in math is Thales' theorem, which wasn't even confirmed to be proved by Thales. But anyway, even if he proved it, that would be like renaming Pythagoras' theorem Newton's theorem because he proved it. Well, anyway, let us start with Thales' ideas, at least in the realm of science. Thales thought that everything was based on water. The Earth was a flat disk floating on a giant ocean. Okay, I mean, those aren't particularly good ideas, especially since there's lots of evidence for the Earth not being a disk. Well, okay. And then, after that, he also had the idea of something coming from one thing. So technically, he is the father of evolution, not Charles Darwin. Why did he think of this? Well, he noticed that everything turned into a something, particularly air or slime. And so, Dali's ideas weren't exactly the greatest, but they were distinguishable from the rest, who didn't even care to explain using more than one word, or rather, a few words to describe the many Greek or Roman gods at that time. Anyway, a few hundred years later, let us go to Aristotle. And around the time of 300 BCE, around the time of 300 BCE, Aristotle was a major physicist. And so, in this era, he was actually a great physicist. And so, his propositions were considered to be fact. One of his propositions was that everything was made out of earth, air, fire, and water. Then what's meat made out of? And then he also thought that, just give me a second. So, Aristotle also thought that everything was pushed by an impetus. What was this impetus? It was the sort of energy given to objects. And so objects purposely stop because they are tired. They have low energy, which isn't exactly right. Okay. So you see all of these three things. However, now I want to ask him one question. What happens in a car crash? Oh wait, Aristotle doesn't know about cars. However, his ideas were still great for the time because everybody was still pounding God. Nobody had learned from Thales. So, everybody was still pounding God. There was no listening to Thales. So Aristotle's ideas were revolutionary for his day. However, one of his most impactful ideas was the idea of heliocentrism. He is one of the first wide figures of heliocentrism, and so he was the one who set up the Christian church for 400 years, or rather, that would be 1800 years. So this amount of time was substantial, and it's actually scary to see how long his ideas persisted. So Aristotle was a leading figure of heliocentrism and had some funky ideas about physics. Okay. Now, the Christian Church really liked Aristotle and Ptolemy's model. Ptolemy was another scientist around the 200s AD this time. And during this time, he wanted to model the Aristotelian. He wanted to model the Aristotelian hypothesis. So, even though Aristotle was long gone and maybe wouldn't have approved it, Ptolemy set the Earth at the center, human selfishness, then put the moon at the first orbital, the sun at the next orbital, then the final planet in that other orbital, and fixed not moving stars except with rotation in respect to the Earth, stars, all orbiting around Earth. What causes us to be so selfish? However, this was definitely not right, at least with our knowledge of the universe. However, Ptolemy and Aristotle thought that with ellipses it could match the observations, so why not try it? And the Catholic Church really liked this idea because it left lots of room outside the last fixed star for heaven and hell. And so it met accord with scripture. And so it was largely accepted. And so the Christian church kept these ideas for 200 years. Or, if you do the calculations, actually 1300, or maybe if you go up to 1972 when this case was solved, 1600 years. So the church couldn't stick on to its ideas forever, right? Oh God. Anyway, let's just okay. So the first person who anonymously rebelled against geocentric rule was a Polish man named Nicolaus Copernicus. He anonymously published a book in fear of being branded a heretic by the church. He published a book anonymously with no author, or at least no author title, and this book talked about proof for heliocentrism and the debunking, sorry, couldn't find the word, of geocentrism. So now, they didn't get in much of a fight because, one, it was written anonymously, and two, in public, Nicolaus Copernicus still had good relations with the church, especially because his uncle was a high-ranking official in the Church of Poland, and so he never faced any punishment. However, his punishment, at least arbitrarily, was that nobody cared about his ideas till 100 years after he died. Anyway, in 1578, Galileo was born. Kepler was born on an I don't know date. However, Galileo and Kepler were both great scientists. You may know Kepler for his 3 laws of orbiting and 3 laws of orbitals, I guess. And you may know Galileo for a lot of things, including preceding Newton, studying free fall, studying jumping off the Tower of Pisa with an apple, things like that. And so he studied lots and lots of things, and both of them were truly great men. And so one day they filmed about heliocentrism, and Galileo really liked this hypothesis over time because heliocentrism was so much simpler. Then came something that was the nail in the coffin for the Ptolemaic model, though it was still possible to believe in geocentrism. What happened was that one day, Galileo observed two, or rather four, weird-looking things orbiting Jupiter. He knew it. Those were moons. And what he didn't know was that there were actually about 17 times that amount, just waiting for him to be just waiting to be discovered. However, there aren't really 68 if you don't consider asteroids moon. Anyway, there were so many moons left for him to explore. However, he had already seen proof that not everything has to orbit directly around the Earth. Still possibly to believe that the moons were orbiting in an extremely absurd path, which made it appear like they were orbiting Jupiter, a path that is sort of swirly. I can show it to you when we ask questions. And this would be the path that the moon takes. However, the Catholic Church didn't accept that idea. And so, Galileo was a suspected heretic. His book on heliocentrism was also banned for 200 years. However, he was sentenced to not the stake because he wasn't a formal heretic. However, he was sentenced to house arrest for the rest of his life, and he died in his house. Anyway, after that, there were many more scientists yet to come. However, I feel the greatest continued on with his legacy of gravity and freefall. That person was Sir Isaac Newton, the person that wrote the book that inspired me unknowingly to fall in love with science. Sir Isaac Newton, when he was young, was born to a single mother because his father was rich, dumb, and died 3 months before he was born. And so he was taken care of by a single mother. Just kidding! He was shipped off to his grandparents at 3. And so he distinguished himself from other children by building these big things like windmills or sundials. They were just models, but they were still great for a young man like him. So he distinguished himself from many others by doing these kinds of things. Alright? And this made him truly a great man, a great mind, and a great student. And so, Newton was a renowned scientist. And he dabbled in a little bit of everything, including cell theory, where he argued with Robert Hooke over a single paragraph, optics, where he stuck a needle in his eye socket, and he was also dabbling a lot, perhaps, in gravity. Anyway, let us look at his ideas of gravity. In 1665, when he was 22, he was working on calculus and stuff like that. And then he was sitting on an apple. He was sitting in an apple orchard, being contemplative, obviously alone. Why? There was something kind of like the Black Plague. There was something like the Black Plague. And so, this Black Plague, it had before killed lots of people in the 1348 Black Death. And it was back. It's actually called the bubonic plague, forgive me. And when the bubonic plague struck London in 1 year, it single-handedly killed 75% of all Londoners. That's a lot of Londoners. However, Sir Isaac Newton, by staying isolated, presumably in an apple orchard, he was quarantined. Okay. So, Sir Isaac Newton in quarantine saw an apple fall right next to him. And he, for the first time in his life, surprisingly, he wondered, why does this apple fall? Why have I never noticed it before? He even said in his books that he was inspired by the apple falling from the tree to get the concept of gravity. Sorry. And so, the concept of gravity was a strange one for the people of the time. It was a strange one for the people of the time. And the gravity had not ever been seen before as an idea. Instead, gravity was completely new. And so, back in the old days, Galileo had discovered that free fall happens at a sort of quadratic rate, or an inverse square rate, which means that it happens at 1 over something squared, or 1 over x squared, let's say. And so Newton tried to generalize this for all objects in the universe, and it sort of worked out. He thought that the reason apples fell and stuff was that there was a force attracting us. There was a force that was attracting the Earth and us together. So, say I jump. What's the reason I come back to the ground? It's because of gravity. And so, gravity is what is pulling me down. Gravity is what's pulling everyone down. Not emotionally, but rather physically. And so, there isn't really a concept of down when you look at the cosmic scope of outer space. There is only next to, you could say. And so, when I jump, I come back down because the Earth has so much mass that I am pulled towards it. And think about it. When you are jumping, you are always facing deceleration. You can post questions in the chat, I'm fine with it. I'm seeing the argument right now, and it's a bit distracting. Sorry. Okay. So, let us continue where we left off. Okay. So, Sir Isaac Newton, okay, where did I leave off again? That would be, okay, so Sir Isaac Newton thought this was a force for everything in the universe. He even wrote an equation for it. How audacious. His equation was that the force of gravity was determined on a simple constant time the mass of one object, the mass of another object, and dividing that by the distance between the two object centers. That's why black holes, which we will talk about later, okay, black holes, which we will talk about later, have so much pull, and why the Earth, sorry, I'm a bit sick, as you can see here, but it's gonna be okay. Phew. Okay. So, Sir Isaac Newton was audacious enough to even write an equation for this stuff. Wow. And so, well, okay. So, he has a few questions that we will cover at the end. And so, now, we will start where we left off, sorry. Okay. Finally, Sir Isaac Newton's ideas were extremely accurate, at least at those times. But over time, his ideas started to dilate, though on the cosmic scale by only about 0.0001%. However, scientists want new ideas, so they thought that there must be another component. They thought that there was a new something. What about the gases? So, okay. Now, Sir Isaac Newton was truly a great physicist. And a few years after his time passed, in 1770, a similar process of forming an equation culminated. A few scientists in 1750 had discovered that there was an inverse square relationship between the electricity, there was an inverse square relationship between the electric attraction of two objects. So, Henry Cavendish tried to do the same thing that Sir Isaac Newton did, but tried to match it with the observation. And so, strangely, it matched nearly exactly with what the gravitational force equation was. It said that the force of electricity was a constant, K, not G this time, times charge 1, charge 2, over R squared. So it's nearly the same exact thing. Just the numerator symbols are changed, and this one constant is changed as well. I mean, the quantities they represent are largely different, but still, they strangely look exactly the same, which I find amusing. Anyway, after that, this equation was all discovered by Henry Cavendish, and he never published it though. And his findings were only published about 100 years later, in 1879, which was coincidentally when Einstein was born, by another famous physicist named James Clerk Maxwell. Sorry. Okay. And so, now, Henry Cavendish, because he didn't publish it, somebody stole it and published it. I mean, the world of science back then was competitive, you know? So after that, in 1785, Coulomb, another scientist, just grabbed all of Cavendish's ideas. Obviously, it didn't work like that, but he still plagiarized from Cavendish, and he published it. So he did easy work of Cavendish, and probably a job too. Anyway, Cavendish was known for a lot more things, including the Cavendish experiment. But he was the actual person who founded Coulomb's law. Not Coulomb, but anyway, well, that is certainly angering and unamusing. I guess things have to work out the way they work out. And so, Coulomb's law, or Cavendish's law rather, it states, as I said, that the force of electric attraction between two objects is equal to a constant times the quantity of charges the two objects divided by the distance between these electric charges. Okay. So, now, oh jeez. Okay. Now, this is only the beginning of the speech. Or the lecture. It will take about 20 more minutes. But, oh jeez. Okay. So, let's see. So, Coulomb, a French scientist, stole Coulomb's law. However, we still routinely call it and use it Coulomb's law today. Even back then, I tried to research if Coulomb actually made the law, and I thought that the answer was yes. But a few months ago, I asked it to Google. Google said no. I looked for all the sources, and there it was. Henry Cavendish had written it down first. Anyway, this electricity alone was an interesting subject, but it seemed like everything was at a dead end. How could there be more development? Well, let us jump to a Danish classroom around the 1800s. Sorry. So, okay, just ignore that sound. Anyway, sorry for the interruption, folks. I'm pretty sick. Anyway, okay. So, let us go to a Danish classroom in the 1800s. In the 1800s, there was a scientist named Hans Ørsted who was interested in electricity and magnetism. And since all the discoveries of Coulomb and stuff like that, not really Coulomb and Volta and Ohm and all these great scientists, he was so interested to study them himself and show them to his students. And so, one day, he left a compass near a wire in his classroom. And when he turned it on, the compass deflected. And he was curious as to why, it was deflected. So, after class, he got a bunch of compasses. I'm not exactly sure how many, but he saw that they all deflected. This experiment you can try. However, be sure that you have a lot of electricity because you will need lots of magnetic field to divert the tracks of the compass needle. So now there was still no reason to believe that electricity and magnetism were connected. It just showed that electric current can generate a magnetic field. However, the scientists of the day saw electricity and magnetism as being connected and an ad hoc hypothesis. However, it turns out it can do much more when connected. Just look at what Michael Faraday did. Michael Faraday was the person that first established the idea of, you could say, electromagnetism. And so this idea was the idea that electricity and magnetism were connected. The opposite of what everybody thought at the time. How did he get there? Well, first, he was accepted to Sir Humphrey Davy's chemistry class, even while only having basic literacy skills at the age of 14. Imagine being in a third grade classroom at the age of 14. Oh, jeez. So, anyway, and still, he was accepted into Humphrey Davy's chemistry class. And after not long, he worked under Sir Humphrey Davy. However, Sir Humphrey Davy fell off a wall. Sir Humphrey Davy had a great fall. And so, Michael Faraday got out of his class and instead started experimenting with his own world, with his extensive knowledge of chemistry. So, one day in 1831, one day in the August of 1831, needed to phrase that correctly, just irking me. Anyway, one day he went and grabbed a copper wire, wrapped it around an iron tube, took off the coil, and then he put a magnet through the copper coil. And he saw that the magnet generated electricity by induction. So this was created by an electromotive force, as Faraday called it. This electromotive force was generating a voltage or a difference in potential in the copper coil, which presumably led to electricity. That's why if you say that this was cotton, or said something that's presumably not a good conductor, or not a good inductor, or something that generally isn't good in generating electricity, like say glass or plastic, or like this tissue box, which is also made out of plastic. And so all of these things are not as good for induction as copper coils or any sort of metal. They can't conduct electricity as well. And so this was the idea of induction. And this was taken even further by Maxwell and his four equations. So Maxwell, who I mentioned before, wrote 4 equations that connected electricity and magnetism. And obviously I won't explain all of them in full detail, but just for a beginner start, I will explain them like this. The first equation basically states that the charge density of a field. So the first thing states that the electric flux out of a field is proportional to the electricity stored in a Gaussian surface. A Gaussian surface is basically a 3D thing. So if you take a little cross section or a little section of that a 2D sector of that thing, then you could measure the influx of electric flux coming out of there. And you can also measure the area which you need for the flux by using something called a line integral, which basically takes the surface area of something and splits it up into many little pieces and finds the area of each one so that it can find the surface area in total. It's pretty helpful, but also pretty complicated. Anyway, that is the final thing we will talk about before we jump to relativity. Why? Well, Einstein was inspired by Maxwell to create relativity or imagine relativity. For one, Maxwell's equations, even though Maxwell didn't realize it, proved to Einstein that there was no such thing as going faster than light. So that means that we cannot evade the universe's expansion, and that means we will only get 6% of the universe. However, that's still enough for us to play with. Oh, geez. Anyway, okay. So let us, where was I? Okay, so for one, Maxwell's equations proved to Einstein that there was no such thing as going faster than light. And the second thing was Einstein was generally just inspired by Maxwell. How cute. And so, this leads us to relativity. Relativity is a complicated subject. So we first need to talk about the principle of relativity. At least that's what I believe it's called. It's really just a reference frame. So basically, let's say that you are biking on the street at 15 mph. Or India doesn't use miles, does it now? Meter per second. And then you have this guy in a car who's presumably not paying attention, who's going 30 meters per second. And after that, you have this guy just watching you on the street, and this guy is just standing there. He's 0 meters per second. And so, when you look at the homeless man, or presumably the man who is watching you, he doesn't have to be homeless, you see him at traveling minus 15 miles per hour, while you are traveling at 0 miles per hour. Or, oh gosh, I messed up the units again. 0 meters per second, while the homeless man you see is traveling at minus 15 meters per second. And so, this is the concept of reference frames. And so what speed do you see the car traveling at? Well, you see it traveling at 15 meters per second, while the car sees you is traveling at minus 15 meters per second. So how does this all happen? Well, reference frames. Basically, you have your speed, and so with respect to the Earth, your speed is 15 meters per second, and the man on the street speed is 0 meters per second. And so, what you do is you subtract both sides by your quantity of velocity. That's how you get what you see the other side to be. And so, let's say you're looking at the car, since you are traveling at 15 and the car is traveling at 30, subtract 15 from both sides, and you think you're traveling at 0 and the car is traveling at 15 because you're catching up with the car by the second. And so this is the principle of relativity, or just reference frames. Anyway, finally, let us get to the final topic. Black holes. This took unexpectedly long. However, black holes are a very interesting subject. So, first let us talk about what happens when you go to speeds that are very close to light. There are three things that happen: time dilation, length contraction, and I'm not going to mention the third one because there's a controversy surrounding it. Okay, so time dilation basically says that when you travel too fast, time is dilated. I really like the spaceship example. When you're watching a spaceship with a glass mirror and the laser fly at light speed across the sky, and it has something to do with geometry and the Pythagorean theorem. There's also something called a light clock that can demonstrate this. But I don't think we have time right now, but I will also elaborate when we ask questions. Okay, and so finally, length contraction is kind of the same thing, but the opposite. If time dilates, then length must contract to keep velocity the same. Because remember, the speed of light must always be constant, except if it's entering a different medium. And so, this is time dilation and length contraction. And so, finally, let us look at black holes. Okay, so this is the culmination of all of it. Black holes are one of the strongest gravitational bodies in the universe, if not the strongest. There are different types of black holes that go spin, and black holes that are stationary, big black holes which are supermassive, and smaller black holes which are stellar, lots of types of them. Typically, if they're smaller, their event horizon is way out of their visible. Their event horizon is way outside what seems to be their visible boundary. However, if you have a supermassive or stellar black hole, then usually the event horizon is a few seconds after you've already entered the black hole. So, why are they so powerful? Well, if you follow Newton's rule, then you'll see that they are so powerful because they make the distance between you and their center extremely small. They are extremely small in terms of size. If we were to shrink Earth down to the size of a black hole with escape velocity above light, which most of them do, all of them do, then it would be the size, it would be 1/10 the size of the smallest marbles. And so, just to give some perspective, it would be around 8 or 9 millimeters. So, this is, I feel like they are absolutely, they are a massive subject that should continue to be studied. Especially if you've seen that video that was captured of a black hole eating a star. So, finally, I feel like this was a cohesive history of science. Also, there is also quantum mechanics and advancements in biology, but for physics, physics including quantum mechanics, I feel like a history of all of the really important stuff. And here, at least for me. And so, there will hopefully be many more discoveries in many years' time. But for now, well, we'll just have to wait and see. So, I feel like that may be it. And now I am ready to answer questions. So, the first question I saw was, okay, cut the man. Okay, so, all right. So, why did other people? No. Okay, why? So supernova occurs when a star collapses, and when a star. Okay, supernova occurs when a star collapses under its own weight, right? I saw that about half an hour ago. Yes, that does happen. Supernovas occur when a star collapses under the force of gravity. And so, when this happens, it either becomes a black hole. Oh, geez. It either becomes a black hole or something. Whoa. Oh, geez. It either becomes a black hole or a neutron star. So, there is a lot of. Okay. Why didn't other people know about gravity? If there was no gravity, we'd be floating in the air. Well, that was because they thought they didn't really bother to look outside the Earth. They knew that there was something pulling them to fall, but they didn't think that it extended to the cosmic realm. Okay. How can the heart have enough blood pressure to pump the blood to the lower part of the body against gravity? Second question to you is, how can a supernova completely destroy the star? So, number one, the gravity actually helps the heart push all of the blood down to the lower parts of our body, like our legs, our arms, say, and stuff like that. And now, the upper part of the body is interesting as well. Okay. So my second question to you is, how can a supernova completely destroy a star? As I elaborated before, it's because it collapses due to gravity. And so, doesn't really destroy a star, can explode into a neutron star or a black hole. Okay. What according to you is the most exciting or interesting discovery you have made during your research? What makes it so special? I feel that my first equation that I made, which was something about recursion back in 2020 April, was my biggest discovery. Now I've completely forgotten it, and there's this other equation that's been on my mind. But I think it makes it. I think that what makes it so special is it shows my first progress in becoming a mathematician and scientist. Can any material cut the magnetic force? Good question. What would happen if you put another Earth on a stable orbit from the Earth? Will it replace Earth or cause the other planets to go rogue? Well, first, let's think about things like binary stars. They have same weight. However, Earth probably won't work like that. If you put another Earth at a stable orbit, if you put it in a stable orbit, it would have to be really, really far away for it to not be pulled in by gravity and crash into the Earth. And if it was that far away, it would probably cause the orbits of other planets and the other rocky planets to go astray. So it would definitely affect the orbits of the rocky planets and maybe also the moon. But I don't think it will affect the gassy giants as much. So thank you for the question, Taniska. First debate, okay, that would already been answered. Time travel to the past and future possible by traveling too fast and too slow. So can we do it without length contraction? Let me just give you a paradox that shows that time travel isn't possible. Let's say that you go to Einstein's time and give him the technology of today. Then he will develop even better technology, and then you have better technology to show to him, and it becomes a looping paradox. So you're visiting him infinite times, even though you're only visiting him once. So that is not exactly good. Okay. There is quite a few messages, and I don't think I can answer them all. So I will only answer a few.
Okay.
Sorry. Okay.
You want to take up few more questions, Professor?
Yeah, just a few.
Okay. We'll just have a break. We'll have two questions and then we'll continue with the chat box. Okay. So Edward, can you please?
Okay.
Professor Bari, I said Gauss had found the essential link between electricity and magnetism using his compass experiment. So my question is, do you think in the future such a link can be found between gravity and electromagnetism?
That is an interesting idea, especially considering that gravity and electricity have a very, yes, gravity is a force, have a very similar equation, then there may be a connection between them. Also considering that gravity is an attraction, and so is electricity, I think that there could very well be a link formed between gravity and electricity, which will link gravity to electromagnetism. However, right now they stand as two separate forces, and the force of electromagnetism is shown to be quite a bit more strong than the force of gravity. So it's a good idea, but without more research, I wouldn't suggest that those two are connected.
Thank you very much, Professor.
Yeah, Utkarsha, you can proceed.
Yes, ma'am. Good evening, Professor. Thank you so much for such an insightful session. My question is that I would like to know more about quantum gravity and what led to the discovery of this idea.
Oh, well, quantum gravity? I believe that is linked to quantum mechanics, and I don't really study much of that. I study more classical physics, gravity, and I also study relativity a little, and I also study, I'm working on currently the theory of everything, but don't expect any results when I'm like 10 or something. However, what is string theory? Basically an attempt at the, okay. So, with Karsa, I think that quantum mechanics is a very interesting subject. But the farthest I know about it right now is basically superposition and probability. And quantum gravity is a very interesting subject for sure, and it can tell us a lot. And quantum gravity, if I'm correct, is kind of like gravity on the microscopic or atomic level. And so I'm very interested in that, and also curious if there is a force somewhat like gravity inside the quantum realm. But I do not have much to say on it right now. Oh, geez.
Okay, sir. Thank you, sir. Thank you so much.
There is an influx of messages. So, thank you, everybody. It has been an honor speaking to you, and I honestly could not have a better experience.
That's so nice. So should we move on now?
Yes.
To the conclusion? Yeah, okay. As we draw to an end to this memorable event, we have the closing remarks by our Vice Principal, Ms. Preeti Sutta ma'am.
I believe you are muted.
So much, Professor. I was on mute. And a very good evening to everyone. It has indeed been an engaging evening of physics in the august presence of the young Professor Suborno Isaac Bari and his revered father, Professor Rashidul Bari. This event has been a culmination of a journey that began in the month of June 2020. As we were busy scouting online for learned achievers in the field of science to interact with our young students and to motivate them, I think it was our destiny that we chanced upon many YouTube links showcasing the impressive and awe-inspiring work and achievement of the young child prodigies, Professor Bari. We connected with Mr. Rashidul Bari, and almost immediately, to our delight, we got the confirmation that Professor Bari had graciously accepted to be a part of the Science Week at DPS Bangalore East to address all of us. And without a doubt, I know that this has been an extremely motivating session for the young as well as not so young learners like myself. Professor Bari, I speak on behalf of all present with us this evening through Zoom and those who are watching us live on YouTube, that we are in awe of your confidence and the calm demeanor with which you convey your thoughts and answer queries. You truly inspire us.
Thank you for such kind comments.
We really appreciate you keeping your appointment with us in spite of not being very well. Thank you once again to Rashidul Bari for facilitating this, and Professor Bari for gracing us with your illuminating presence. It's truly been an honor. Thank you.
Thank you, ma'am, for your guidance and support in planning and executing this event. It was just amazing, Professor. The ease with which you explain makes the subject enjoyable. You have a magnetic personality and a very charming smile. Wish you the best in all your endeavors and services.